And welcome back to another exciting segment of physics at the Mars Flipped Physics Classroom. And what we're going to do today is continue in still the first section of Chapter 1, Mathematics and Physics. But we are going to, after a little review, move into some other topics. We're actually going to talk about dimensions in physics. What is a dimension? And some of the units with which we measure dimensions, the constants that are used in measuring dimensions. And we'll show you a very, very important thing called dimensional analysis, which is really important. These units, the SI units, are used throughout the world. And since we have a global market, a global economy, it's very important everyone knows about the SI system and the metric system. First, some review from Mrs. Adams.
Okay, here's one that people have a lot of trouble with. This has to do with inverses and finding something that is in the denominator, but we want to actually put it in the numerator. So we have to read, first of all, our problem. Solve the equation for Q. So we go over here, we identify, okay, here's the Q. This is the guy I want to get a loan on the top. Okay, so this is what I'm going to do first. I'm going to isolate the particular relation that has the Q in it. So I am going to keep 1 over Q where it is, and I'm going to keep, of course, I don't want to move 1 over F because it's away from the variable. I'm always trying to isolate the variable, but I do want to subtract 1 over P. Okay. Well, you think, oh, gee whiz, now it's kind of weird. I don't quite know what to do. And you can't take an inverse of a sum or difference. So I'm going to move up here just so I don't go off the page. Let's take a look at what happens. I've got 1 over Q here. What I need to do over on the other side is to rename this in terms of a common denominator. It doesn't have to be the lowest common denominator. It just has to have both of these factors in it. So I'm going to say, all right, well, the common denominator would be F times P. Okay? What did I do to this right here to get FP? I had to multiply that by P. So now I'm going to be putting a P in. P times 1 is P. I still have my negative sign. And then what did I do to this thing to get FP on the bottom? I had to multiply the top by F as well. Okay, so that's F times 1 is F. So now let's take a look at what happened. I have the inverse of what I'm looking for expressed as a fraction. That makes it very, very simple for me to do this. Take the inverse of both sides, and I end up with Q, which will have meaning to us. That actually will be the image distance for a lens, is equal to, and I just want to flip these guys, right? Flip the numerator and the denominator. So the thing that's now in the numerator is going to be in the denominator, P minus F. And the thing that is in the denominator up here is going to be in the numerator because I had to flip it to get 1 over. So this equation, solving for Q, is actually going to be Q as FP divided by P minus F. Now you might want to also remind yourself that you want to put this in a parenthesis so that you're making sure that the entire thing is in the denominator. We run into problems with that in calculator land because the calculator is only as good as what you put into it. So you have to tell the calculator that both those pieces are in the denominator. So that's why you generally would like to make sure that you keep that together. Okay? All right. Dimensions and units get all mixed up. Dimensions are going to be things like length, time, mass, all of those sorts of things. Okay, we're going to deal with other dimensions as well. And the unit is feet or inches. You know, if you're in the United States, we're going to be working in the SI system, so we'll have things like meters, we'll have seconds, the actual units of the particular dimensional quantity. So that's important to understand. There's Sistema Internacional de Unité. That is the worldwide accepted value scientific units. Okay? And in your book, you can see that there are 7 base units right here. And we have their symbols. And you are going to be using these base quantities and base units as you go. One thing I want to say before we get off of this slide is if you put a prefix on top in front of one of these, you still have a base unit. So let's say that I have let's say a meter, okay, and I'm talking about a centimeter. A centimeter is still considered to be a base unit. It is just not the base unit. The only one that actually has a prefix as the standard base unit is the kilogram. Kilo means 1,000, so a gram is tiny, right? So that's the only one that actually already comes with the larger, or the larger prefix, kilo. Okay? The meter has no prefix here, but as soon as you get into measuring, you're going to be in centimeters, but it still is a base unit of the SI system. The kilogram and the meter actually have standards that are housed in a building on the geographical region that is France, but actually the land on which the Sistema Internacional stores its standards is a internationally owned piece of property. Just like the United Nations in New York City is not subject to the laws and is actually outside of the United States, even though it's right in New York City. It's the same for the Sistema Internacional building. It is a totally independent authority in and of itself, so that nobody can ever come in and say, okay, now we're going to make all these changes. All right. We're also going to be using, besides the base units that you just saw, derived units, which are basically multiplications and divisions of the base units. One thing that happens in physics is everybody names the derived units for people, and then that doesn't mean anything. So a Newton, for example, is a unit of force. So you're going to have to understand what base units the Newton is made out of. Joule, James Joule, was the person who was the beginning of the idea of energy from heat. And Joule is basically meaningless unless you understand that its base units that make up the Joule is a kilogram meter squared per second squared. Conversions in SI are extremely easy. That's much easier in physics than they are in chemistry, of course. So we're going to be working with the factor label method, and we'll do that in class. And I know you've done it before, so we'll just take a look at a couple things you'll need. In your book, you have the big list of the standard SI unit prefixes and their respective power of 10. The thing to remember is kilo, mega, giga, and tera are bigger, and centimilla, micro, and nano are smaller. And that's the big thing. A centimeter is smaller than a meter. A kilogram is greater than a gram. Okay? Those are the things you need to bring with you to class tomorrow. Prefixes in your textbook, you're going to see very big, very small. Okay? And what we'll be doing, for example, is we're going to be primarily working with some of these that are right here. We'll have something like, usually millicentigram, not much on deci, but kilo. Those are definitely ones that are important. When we get into wavelengths and things, we'll be working with nano and pico. Micro certainly comes into play, and femto is very tiny. Okay, so this goes from the very tiny to the very large. Let's take a look at dimensional analysis, where we can actually see if we have the correct formula. We say in a lot of times that if you don't know a formula, you can always follow the units to determine if you have set up the problem correctly. So we're going to be working with dimensional analysis for a couple different reasons. Dimensional analysis can also help us choose conversion factors. And so this is what I was just talking about as far as knowing whether a gram is bigger than a kilogram. Okay? If I'm trying to take a look at a factor label method, what I basically do is I make a fraction where the numerator and denominator are equal to the same thing. So I understand that a kilogram is larger than a gram, and therefore the gram has the conversion factor. That way I never have to use those negative exponents. If I know that a kilogram is worth 1,000 grams, then I can flip that around any way I need to come out with the correct conversion. And I can work it as a kilogram over 1,000 grams, that's equal to 1, as well as 1,000 grams over a kilogram is equal to 1. That's something I think people forget. Whenever we're dealing with conversion factors, we're just basically multiplying by 1, and then whatever we want to make equal to that 1, 1,000 grams over 1 kilogram, for example, is going to be pointed toward getting rid of things we don't need on our way to getting a transformation that we do need. Dimensional analysis is a whole different horse, though. Dimensions are a little bit more difficult, and we use these square brackets to talk about particular dimensions, so we don't start thinking of them as time being a unit. Okay, seconds are units, time is a dimension, lengths are dimensions, meters are units, as is mass a dimension, and kilograms a unit. So keep that in mind. If it makes sense to you, you're good. So you want to choose a conversion factor that will make the units cancel that you don't need and leave you with what you're supposed to have, as, you know, transforming, for example, from meters to kilometers. If we want to convert 1.34 kilograms of iron ore to grams, all we have to do is recognize that 1.34 kilograms can be multiplied to make our kilograms go away. Okay? So what I've done, and I did that already, is to recognize that because kilograms are on top to begin with, I have to put them on the bottom, and then that means that I'm going to be multiplying 1.34 times 1,000 grams to get 1,340 grams. I think everybody understands that. That is one piece of usually a very long string of conversions, but they all are basically fractions where the numerator and denominator are equal to 1. Dimensional analysis is a little bit tricky sometimes, but they are reminding you that the dimensions are the basic types of quantities that can be measured, like length and time and mass. A unit is going to be the standard amount of a dimensional quantity. So I wanted to make sure you got that already. Scientific notation and significant figures we've worked with in many different science classes, I'm sure. So in physics we talk about the very large and very small, so this becomes extremely important. Scientific notation, keep in mind, has to start with a number that is between 1 and 10, okay, not including 10, And we want to make sure that we have only in this first number the number of significant figures. That's a nice, that the reason we have scientific notation, first of all, is so that we can report our answers very easily into the correct significant figures. Okay? I think everybody has understood that. Here's a practice that I would like you to look at. Okay? Use dimensional analysis to solve this problem. The period of a simple pendulum, defined as the time necessary for one complete back and forth motion, is measured in time units and is given by the equation capital T is equal to 2 pi times the square root of capital L over G, where L is the length of the pendulum and G is the acceleration due to gravity in meters per second squared. What we want to do is to check this equation for dimensional consistency. So let's take a look at what we will be working with, okay? So we start with T equals 2 pi times the square root of L over G. First thing you want to recognize is 2 pi is a constant. Pi is actually a number, right? 3.14 da 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 da. So that is a constant. Constants do not enter in to dimensional analysis, so we're just going to totally get rid of that. And so what we want to do is we want to recognize that the dimensions of this thing, so we're going to use brackets to make sure we understand. We're not talking about actual numerical values, okay? And we want to see if the dimension for time, which I know is seconds, so that's pretty easy, is actually going to come out to be the same as the dimensions for, and just to make this a little simpler, I understand that the square root of L over G is exactly the same as the square root of L over the square root of G. So just in case you want to work it that way, okay? What I'm going to do here is just write this as L over G and then a square root around the whole thing. So just to make sure you understand that, okay? So let's consider. Time, I know, are seconds, so I don't even have to think about that. I know they have to come out in seconds. So what I want to see is if this is going to work, okay? So let's take a look. I want to get rid of this square root, so I'm going to square both sides. So now I have seconds squared, and I just do that. Okay, there's seconds squared. Here is length over G, which is, keep in mind, they told us that G was meters per second squared. That was in the problem. Okay, so I'm going to put that in there. Meters over seconds squared. Okay, well, meters, now I have to get into, this is a dimension, and now I only have one dimension, I have 2 units, okay? So the next thing I want to do is change this last dimension, which is my L, okay, into the SI dimension meter, or SI unit meters. So now I want to do meters over seconds squared. Hey, there we go. My meters and meters go out, and this is 1 over seconds squared, which is seconds squared. And so I say, yes, I have the correct equation for dimensional consistency. Okay? Remember that you want to make sure you're using the dimension symbol with brackets until you replace everything with the units that they are measured in. And then you can see if you're going to get the right units.